Hello everyone, I'm Nicola D'Avanzo, a PhD student from Laboratorio di Informatica Musicale in University of Milan, and I will present you our work on Resin, a vocal tract resonances and head-based accessible digital musical instrument. Resin is an ADMI controlled through head movement and vocal tract resonances. Since Resin does not require the use of hands to be played, it is playable by musicians affected by severe motor disabilities, such as quadriplegia. Resin is a MIDI controller, and it is a monophonic instrument, since it cannot output more than one note at a time. Vocal tract resonances are used to control pitch selection, while head rotation controls note attacks and releases, and playing dynamics or intensity. Its design is motivated by the desire to experiment with these peculiar interaction channels. Pitch selection through vocal tract resonances can be simplified as follows. A set of sine waves having the same frequency of MIDI notes is conveyed to the mouth through an insulated speaker connected to a rubber tube. Placing the tip of the tube and varying the shape of their mouth in a similar fashion as whistling, the user is able to make a single sine wave resonate, thus having a higher volume compared to the others. A lavalier microphone placed on the tip of the tube detects the resonating frequency. The signal detected by the microphone is then fast Fourier transformed. On the Fourier domain, data is filtered through a bandpass, a smoothing and a moving average temporal filters. Then the resonating pitch is detected, thus transformed into MIDI pitch. This is how the algorithm estimates the resonating note. Each MIDI note corresponds to a number of fast Fourier transform bins, defined as a group of bins G. In the image, you can see how notes A, B, C, and D are given a space, highlighted with different colors on the Fourier domain. The mean quadratic spectral energy for each group is then calculated. The estimated resonating note is the one corresponding to the group with the greatest energy. Head tracking, as said, controls notes onsets and dynamics. We built an head tracker on top of a pair of headphones, using an Arduino microcontroller. The musicians should move their head like a violin bow, and the system responds in a consistent way. Head rotation speed on the yaw axis indeed controls volume and pressure, while a sudden inversion in the movement determines a new note onset, or attack. Resin's interface provides some visual feedback by plotting the fast Fourier transform and the energy of the detected note. In the image, it is highlighted in green. The user is allowed to select which notes are playable. They could, for example, select only the notes belonging to the C major scale or a pentatonic scale. Having less notes corresponds to more detection precision for the algorithm, and less playing precision required to the user while controlling their mouth. The user is also allowed to adjust the gain of each sine wave, manually or automatically through a calibration system, to make up for a possible non-flat frequency response of the speaker connected to the rubber tube. The paper contains further details on the interaction scheme and a complete description of the algorithm used and their rationale, especially for resonance recognition. Now some further details and a word on main future works. The software is released under an open source license, and sensors are built using low-cost components. This is to strive for affordability other than accessibility. Playing requires to stay in tune, with no other feedbacks than the visual feedback. Better visual feedback could be introduced. The actual system is good to control some instruments like strings. New interaction paradigms, with or without head tracking, could be introduced. But most importantly, an evaluation of the instrument with users should be carried out, through measured tests and case studies. Thank you for your attention.